always wanted to come here, but the hockey team sucked, so I got a spot on the team over at Harvard and stayed there for a couple of years, and went and played professional hockey. And the day that I got my signing bonus, I showed up at the flight school and started getting my license. And I knew that I was onto something. I had flown a little bit as a kid, and when I was in high school, I designed kind of modified the back of the Popular Science magazine plans of a ultralight into something, but I kept cutting corners, and my mother ended up actually burning the airplane so I wouldn't kill myself in it. And so when I had enough dough to go in and start flying, but it was kind of expensive, I started that immediately and kind of refocused all my efforts towards designing new types of pilot interfaces for airplanes and experimenting with translating the natural motion of the pilot, the same way they ride a motorcycle or walk through the world, into the motion of the airplane. And that's what led me to this opportunity. So I went all up and down the East Coast pitching every investor that I could find this idea of translating the motion that the humans naturally make as they move through the world to keep coordinated turns as they walk or they ride a bike into flying an aircraft. And proved this by putting pressure sensors inside the legs of a motorcycle rider on the feet, some tags on the shoulders, and some strain gauges on the bar, and built full motion simulators with pilots flying from the motorcycle position, which forced them to have a coordinated turn all the time. I pitched that to everybody that would listen, but nobody would listen. But there was one investor who said, I'll fund something else that you have. And I had a series resonant converter, really boring stuff, doing die casting, and started a business doing power supplies for die casting. And then sold that business and started a business doing very large power supplies that would buffer the irregularities of wind farms. And consumer inject real and reactive power to stabilize the grids down in Hawaii. I spent a lot of time in Hawaii. And everywhere I went, I found every excuse I could to fly everywhere that I was going. And then started a business called Design Book that formed teams of people with common passions and complementary skill sets. And my thought was I could form a team to implement this idea around the natural control of an airplane. We got a cease and desist by Facebook, which was awesome. We were in the Wall Street Journal, got hundreds of thousands of users on the app, but we couldn't do anything with it because we were pursued by Facebook because we had book in our name. And I ended up doing a favor for a buddy who knew I liked aircraft. I had spent a lot of time in batteries and energy conversion, and he said, why don't you come on down and do a review of a electric aircraft that is being designed out in California. And I'm telling you this story because it's not always easy to get into the fun side of aerospace engineering. And I showed up, I wasn't getting paid to be there, and I had dissected a paper written by a company doing an electric helicopter. And I presented it, and in the audience was a gal by the name of Martine Rothblatt, who's the founder of Sirius XM Radio and United Therapeutics, both multi-billion-dollar companies. She's a helicopter pilot and a fixed-wing pilot. And halfway through the discussion, there's 20 people in the room, she said, whoa, who are you and why are you here? And this why are you here will come up as a theme. And I said, well, I'm Kyle, I have a little bit of experience in batteries, and I'm here because Scott asked me to do it. She goes, are you getting paid to be here? I said, no, I just thought it'd be fun to talk airplanes and think about flying and think about how we could electrify things, because that's where there's this kind of convergence of some expertise and a passion. And she hit me with 5 or 6 other questions and said, let's have coffee. And this right here is the result of a cup of coffee on a Friday morning just about 2 years ago, where I spent a good amount of time talking with Martine about how to drive innovation. And in something that I was passionate about, which was flying, how to drive innovation in that. And I said, all right, great, let's go. And we went into it. And she said, how would you do this? And I got home and I thought about some of the comments she made. I thought about her approach to things, the practitioner in her. And I said, we just build something. Let's start by building something and let's explore. And let's get the right fidelity of the tool, the right depth of the fidelity of the tool to explore each technical step in the development of an aircraft. And let's set an audacious goal and let's fly across the country with it. So I got home at about midnight and I just painted a watercolor and I wrote all over the watercolor. And this was the very top of the watercolor. And I put a budget in, I put a timeline in, and at 9 o'clock in the morning she said, you're on. And she sent us a couple $1 million and said, go for it. So this is the story of how we did that. And this is a story of just trial and error and micro experimentation at every level to get to where we needed to get. And about keeping our promise. So we had a saying internally, well, first of all, just simple enough to be revolutionary, but every time there was a question, should we go this direction, should we go this direction? Should we do it with a traditional rotorcraft, should we do it with a fixed wing aircraft? And we just kept reminding ourselves, what was the promise that we made? It was to elicit critical thinking in electric aviation. So after exploring 35, 38 different designs, we started to compare things like complexity and criticality and simplicity and range to get to exploit the benefits of electric propulsion and get a practical aircraft. What did we need to do? Well, we need to get it on a wing, we need to have low disk loading, we need to get high specific energy density batteries and low empty weight fractions. And these were the simple levers we knew we needed to pull. And this is the sketch that we used to catalyze the first directional push of the team. And then naturally you need to put together a team. This is our team now. We started with 4 people. Started with 4 people to get to our critical design review. And the first step was putting everything into a simulator. Well, when I was at Harvard across the street, down the street here, I met a guy by the name of Austin Meyer. Does anybody know Austin Meyer? He founded X-Plane. And when I was there and I was telling him about my challenges about taking the angular and linear accelerations out of X-Plane and translate that through a motion queuing algorithm to show that this motorcycle-like aircraft would work, I needed him to change the output of X-Plane so I could do it more efficiently and do it without any latency. He did that. So I called him up and I said, hey, we got a new problem. We got a new problem. We have to model 35, 50 different aircraft. And we know that the hardest thing that we're going to do here is not integrating things, but probably writing the flight controller for it and doing a transition from a rotor to a wing. So let's write a flight controller for each of these, an autopilot to do this. Let's just count the lines of code, and let's just say, how simple is this autopilot going to be to do? So we started doing that, and we started looking at the different transition dynamics. You can see some oscillations on the glide path and final here. These are tracers showing the final approach. And everybody can visualize and see the way a transitioning aircraft can transition out. But has anybody here flown a transitioning aircraft, got into an Osprey simulator or something? The odd thing is transitioning back. It's a thing, everybody just visualizes the obvious step in every problem. But transitioning back when your wings asymmetrically stall, or your rotor's getting to high-speed edgewise flight, while you're trying to slow down and you've got 3 variables in 2 equations where you're saying, I'm going to use my distribution of propulsion to affect the stability of the aircraft, and you say, oops, and I'm trying to descend, so I can only push air down to make airplane go up, and now I'm trying to go down all around. So do I push less over here? I can't reverse this. And this vector is changing, for example, and you're saying, well, my vector's pointed halfway up, halfway down. So if I elicit a control input over here to pick this side up, I'm also inducing a yaw. So as you kind of dissect these different problems on the reverse transition, which is the hard problem, we start to look at the stability of this, and we start to use some metrics to define how efficient of a transition we can get. The pitch, the deck angle, right? How far off the glide slope the thing's going to get. And we started threading these things together. This is Austin, fun guy. And X-Plane, does X-Plane, just to give it a little bit of, get back to the tools. Everybody knows what CFD is here. You guys probably are way more educated than I am on this. But we looked at this problem, we said, well, let's use something called blade element theory. And it's in X-Plane already. And let's augment that a little bit with the things necessary to capture things like coaxial rotors. And this is a flow field, very, very simplistic flow field around an aircraft. And blade element theory, and I won't go through the basics of it, but basically 60 times a second this thing's determining its next state. So we flew this thing, we built simple simulators, we grew up a little bit more, we started analyzing the pilot experience. I think this is a different slide. We got to the point where things were getting super frustrating. We started to write autopilots. Does anybody know what Xavion is? Xavion's an app. It's actually on the App Store. Just yesterday, we released 3D instrument approaches, synthetic vision, 3D instrument approaches to play with it and give us feedback, please. But we used that as a kernel for an autopilot. And we flew more, we put it into VR, and then we started to convince ourselves that this could be an actual product. It wasn't just a fun thing. And we built a network of aircraft and recharging pads all around New York City in a virtual world, and we started flying these things in all different weather and analyzing how these things would handle. So we said, we're going to build this aircraft, maybe we should have a path to doing something with this aircraft. Started building small-scale models. Everybody probably has flown this little trainer. It's like the ubiquitous foam $100 trainer. But you see that there's 4 tilting rotors on the corners, and it takes off, it tilts forward, and we started to explore simple flight control algorithms. We made a bigger and bigger trainer, and then we started to look at how we were going to get the big challenge of moving from a quad or a drone flight controller, which usually has a single point of failure. It's got a single flight controller, it's got a single inertial measurement unit, a single GPS, and one of those fails, things fall out of the sky. And if we're going to put a person in this, then we're going to have to look at redundancy and how we manage that redundancy. And we started to divide up the aircraft and doing something called a fault hazard analysis, an FHA. And we started doing that here. And this is when we started to split these motors, a top motor and a bottom motor. And then you look at the power supply to these things, and you look at 2 different batteries, and you say, if I have 2 batteries, how am I going to spread that across the aircraft, such if I lose one battery, the thing can still stay rubber side down. What failure modes are palatable, which are not palatable? How many people fly a helicopter here? Anybody? Like, main rotor or tail rotor, would you rather lose? Main rotor? Well, you're a sadistic, but you don't want to lose the main rotor. You want to lose the tail rotor, right? Tail rotor, you lose the tail rotor, things are a little bit ugly, you're going to come in 25 degrees at 40 knots or whatever, and you're going to be able to survive that, right? So an uncommanded yaw is something that could be survivable in a drone, right? But a uncommanded pitch or roll puts you upside down and you're done. So when we write a control algorithm, we say, what's my prioritization? First, how do I spread that power? Well, obvious statement, let's put one here, one here, one here, and one here on the top, run that with 1 battery, 1 flight controller. And then take the bottom ones and use a different flight controller, right? Same control algorithm, they have to know that each other exists. Simple. We started looking at airspeeds, of course, and we got all that together. This is our flight controller. Started flying this thing. And I put this picture on here just so you understand how quickly this is iterating. This is like 3-4 weeks in. And we're like, let's get this thing flying. We got it in the simulator, let's get it cranked out. Team comes together, it's 4 of us again. I say, let's build an Iron Bird. Let's construct this thing in the lab. So we start building the Iron Bird. We start running motors back to back. Everybody knows the MRAX motor they use on electric sailplanes. Reinhardt inverters are the ones that win the Pikes Peak every year. Obvious things. Let's throw these together and start working. I grew up in a machine shop. My dad had a machine shop, so we went over there and started cutting parts. And we knew we needed to reduce, in order to get low disk loading, we needed to get big rotors. Motors, electric motors, to produce power, which is torque times speed, of course, you need to get things moving pretty quick, right? To get power density. But now we need torque density. So what's the easiest diameters in axial flow rotors, in a tilting rotor, gets pretty ugly, right? It's like a radial engine. So we started to design epicyclic gearboxes, and you can see some pieces here. McLaren said they could produce these for us, harden them, buy new materials, and they dropped the ball. So we quickly pivoted and said, we're not going to drop the project, we're going to keep our promise. We started building carbon belt drive systems. We wired up the Iron Bird, and this is the beginnings of an Iron Bird. And you can see these cartridges here with 2 inverters, 1 radiator, which is hydraulically separated, and 2 inverters on each end. I put this up here. This guy, Steve Arms, on the left side. He started a business in sensors. He made IMUs that Airbus uses, a whole bunch of folks. He heard what we were doing, and he said, holy shit, you guys are having fun doing this. You're loving what you're doing. You're a bunch of artists out here doing this. I want to join the team. We had more than half our team not getting paid, diving into this program with so much passion, and that smile captures it all. Same thing with Dave Churchill on the ground here. We got to the point where we said, what are the two things we cannot tolerate? Rotor failure or separation, and a battery fire. Battery fire, who's been around a lithium-ion battery fire? Anybody? Probably 5 of you. This pack right here in testing, we had a cascading failure, 5 cells, and of course that just lit off the rest. I unloaded 7 canisters of fire extinguishers into that battery, and it doesn't put it out. There is a lithium-ion battery fire is untenable. Put those into packs, and this was our Iron Bird. You got a cockpit, you've got control systems, you've got pedals, you've got complete avionics, redundant motors. Those 2 inverters, like I said, are completely separate electrically. Different controllers, different batteries, different liquid cooling systems into the motors, and because we got a short change on the gearboxes, put belt drives on. We said, all right, well, we got to shove this into an aircraft. So we started to just hack together a CAD model. We took a Lancer ES. Who knows what a Lancer is? Yeah, they're all over Reno Aero races, right? High-speed records, are very slippery little planes. And the efficiency of going from sketch to model, no drawings. Simple concepts on cooling. Very, very basic first principles things. When we got to the components that we said we couldn't fail, these outriggers that reach out the front of the plane, start vertical and tilt forward as you fly forward and then come back to vertical to land, we knew those were going to be really hot items and like they need to be designed. 64 pounds, that's a carbon outrigger looking at a 4,000-pound plane. Put strain gauges on them, flex the thing, move the thing. We built vibration test stands, and then we took our airplane, we chopped the tail off it. Anybody know why we chopped the tail off it? Anybody know why they have drooping flaps on a V-22 Osprey? Everybody knows why, right? Because of the downwash of the rotors. They have these massive drooping flaps on the outside. And ailerons or flaps, whatever you want to call them, flaperons. We couldn't have a traditional tail because those rear rotors would blow down on the tail, change the incidence, then it becomes totally unstable in pitch during transition. So we chopped the tail off and designed a new tail. The new tail is a T-tail. Everything about the donor aircraft was out of square. I was hoping there was a wing picture in here because we put in, there may be one coming up. Built battery boxes, again, weight is king in airplanes, it's just compounding. Put this carbon trash can across the back to hold the races of the bearings. This wing right here, holding up a 4,000-pound airplane, was initially rated for a 220-knot airplane. We slowed this thing down to about 120 knots. We were able to go from 350 pounds, take the fuel system out, put a lighter skin on it, take the de-icing off the front. So we just put inserts in existing molds and pulled the carbon wing off of here at 250 pounds. That entire wing is 250 pounds, which is awesome. Put the outriggers, you guys starting to see the visualize how the aircraft's coming together. Outriggers on it. This could have been the smartest thing we ever did. And if there was one thing to take away in aircraft design, is don't do what Learjet does. And if they put a battery in the back of a Learjet, they'll put the battery on a dumbwaiter and they'll suck the thing back up into the tail. Now you've got a dumbwaiter, you've got a pulley, you've got a cable, you've got all these retainment systems, and you've got this battery tucked way in the tail. We said we need to service this thing. So this gun cartridge right here is on 3D printed rails, and you just slide it in there. Literally, you can complete a flight and rip it out and put a thermal camera on it. And look at the entire profile of that system right there. But when you're servicing it, it's in and out, in and out. And in the middle there, you see the air inlet and the air exhaust and little 3D printed ducts that force that air through the system. EMI issues, these are just sketches that were on there. You saw the belt drives, put the props on the aircraft. In electric aircraft, who remembers the movie Armageddon, the worst environment imaginable? That's what this is like for controls. You've got permanent magnet motors, not a lot of iron, right? Basically no iron. And you've got these really, really high frequency systems because you want to keep, you drive really low inductance motors, 30, 40 kilohertz inverters, and then you're trying to get really high integrity data out to your inverters. Really high integrity IMU information back. Really high integrity fly-by-wire systems, because in Hangar you're always in fly-by-wire, right? And the shielding, you can't solve it the way that if you work for Raytheon, you're building a ground-based missile system, and they're like, hey, EMC, we can get it down to here, and you're like, that's easy. We'll put shielding, we'll put ferrites, we'll cover this whole bugger up, and we're done. You want to fly with that? All of a sudden, you take all the weight out again, right? So how do you start shielding things? And you have to use innovative tricks. You have to understand the electromagnetic noise in order to attenuate it. And all of a sudden, you're decoupling things with capacitors, putting silver paint on things. And you're getting to something that adds grams instead of pounds for every one of these solutions. So I know I changed the dimensions. Not the dimensions, the unit. We had a lot of issues with bolts and vibration and shearing off. We took these things in and out through ground power tests. We had hundreds and hundreds of ground power tests. We were totally committed to shake this thing to death before we put it in the air. Galling was a big issue. Aluminum pieces, they get next to each other, any motion just galls the snot out of them, and all of a sudden they get really sticky, and they basically friction weld themselves together. Batteries, again, we wanted to make sure that these things were thermally stable. So we would run the thing, we specifically designed the cowling so we could take the cowling off real quick and take thermal images of it. Make sure that our surface temperatures were what we expected so we could predict the internal temperatures. You can't put thermocouples on every cell, and you have 15,000 cells in here. You're going to poke them down in a couple spaces, you do an FEA on it, you calibrate that FEA against what you're getting, you look at the surface temperatures, and you start to understand it. Traditional airplanes, right? We've got cowl flaps, we've got mixtures, we've got prop settings, we've got all these things that we're super familiar with. What are the critical things in an electric airplane? You got to keep the controls power alive, right? You have to keep how many people shut the master off on their buddy while you're flying, right? You're like, oh, the shit's still running. Right? You can't do that in an electric aircraft. You've got to have controls power. So you have to rethink the way things are designed. So this is just a sampling of the different things that go into there, and then when you're test flying the thing. Let me give you an example of that. If you have a Tesla car, anybody know that there's a fuse in the back of the Model 3, you pull the floorboard, you can see the fuse ring. You think you'd ever tolerate something like that in an electric aircraft? How do you want things to fail when you're in the air coming on final approach into Mass General? Probably want to keep the power on, right? If something fails. Do you want a contactor that latches closed or latches open? Probably latches closed. All the things are the opposite of what you want in automotive or in industrial design. So you have to rethink all this logic. And then when you're test flying the thing, when we test fly like a turbine aircraft, you're looking at pressures and speeds and temperatures of the turbine, you're looking at fuel flows, and here, you're not looking at any of that. The second most important thing, I would argue, would be your CAN bus load and your CAN bus drop rate. Things start to get messy on that CAN bus, and you've lost control of the aircraft and you're done, right? You're happy to run out of batteries in this, but you're not happy to have something go full torque, one direction or nothing, right? So we're looking at completely different things while we're flying, and I apologize for the picture here, but that whole center display is looking at fly-by-wire systems. Another big thing that you learn when you're flying this type of aircraft is, as you go through transition, the inertial measurement unit, remember the inertial measurement unit and the fly-by-wire sensors coming off the pilot. Let me talk about that for 1 second. So up here, you'll see a little cam here. On the other side, there's another cam. There's some string pots under here. Geographically separated, there are 3 sensors for every axis of input. So if the pilot wants to roll, the flight controller is getting information from 3 different sensors. Just in case his foot went up underneath there and kicked this, or you had a hard landing, your elbow came down and broke something. These are practical things that happen all the time in flight tests. You need to have these geographically separated 3 to 5 sensors, depending on who you ask, and you vote on those. And those voting algorithms have time considerations and magnitude considerations, and they forget about things that happened a long time ago if you're in a different phase of flight. It's not super simple how to vote on things, but what happens is you feed into the flight controller what the pilot wants to do, and the inertial measurement systems are feeding into the flight controller saying, this is the attitude I want the airplane at, And if you have a position-based control versus a rate-based control, in this plane it's position-based in roll and pitch, and rate-based in yaw, then you can easily mask your control margin with the IMU. So you could sit there with the position forward 30 in a traditional aircraft. If you're flying along and you're like, holy shit, I'm all out of elevator. You know when you're nearly out of elevator. There's nothing else in the equation, right? You don't have an IMU saying, oh, I'm going to trim you up a little bit to get to a position, right? In this aircraft, you could be pulling it back 20% of its throw. Let's say you're trying to raise the nose on the aircraft. The IMU is saying, hey, I'm not raising, so I'm going to now increase the torque on the front rotors, decrease it on the back, increase the torque on the front, decrease it on the back. And I'm sitting here happily at 25% of my throw, thinking I got more margin in the stick, but masked by the IMU, we're completely tapped out in torque. And you can very easily do that in yaw, if you have clockwise and counterclockwise rotors spinning you around, and all of a sudden you want to perform a secondary maneuver, and that's why you have to prioritize those things. So you get into flight test here, and you need to know that. And that center thing right there shows you the margin that remains as a function of what you're putting in as a pilot and what the torques are coming out. When we were ready, we started getting the cockpit ready, put some super safe devices in there, looking at temperatures of everything. Temperatures are one of those things that will just kill you if you get it wrong. The motor, this is a little bit of diversion. So propellers. The propellers in this aircraft, we went to 35 different manufacturers. I'm like, what are we going to build? What are we going to buy? Obviously, we're going to buy propellers. Everybody makes propellers, right? We went to 35 different manufacturers of propellers, and they said, you're crazy. A fixed pitch, edgewise flight rotor, 11-foot diameter. We're not going to make that. Half of them were liability. The other one thought it was, just stupid. So we said, we're going to build our own. So we started to do some really basic models. We went to the internals of the propellers, to reading about propellers. Anybody know about the fatigue life of propellers? And aluminum, carbon, or composite versus wood? What's interesting about that? That wood is the only material without an FAA-rated fatigue life. It'll run forever because of the drain boundaries and the damping coefficients of the material versus the way that you stress composites. Really interesting. So we said, okay, there's something there. And one of our bigger risks is the vibrations. So let's get something in there that dampens vibrations. Foam isn't very good, but wood's pretty darn good. So we started with a wood core. We stacked up the wood, and in the interlayers, we were looking at the centrifugal force calculations. We're saying the wood isn't quite strong enough to hold it out this way. So we used unidirectional fiberglass in between every layer of the wood. People wouldn't machine these things, so we brought it to a furniture maker. We said, put this on your big machine, build this out. Once we got that done, we peppered the things with strain gauges to validate our Excel spreadsheets, Microsoft Excel. Put wireless transmitters in the middle, strain gauges, those are all rosettes out there, so we didn't have to know what the direction of the strain was. We could just lay them down, spin the things. We brought these things to failure. This is just a static test, right? So you've got centrifugal force, you've got drag forces on the thing, and then you've got this bending force in the aircraft, or the propeller blade that's causing lift. And we're hanging these things on here. We got to 10 times factor of safety, was our target for the rotors, because we were unwilling to compromise on a rotor failure. This was the ultimate test, is to hold somebody up, right? Got to UV coat the things, and we got into the dynamics of the thing. We wanted to look at the flutter of the rotors, right? These are going to be an edgewise flight. We spin them in this cage. We put strobe lights on when we're ready. We put them on here. Edge wear in the propeller was a big issue. We met every morning. We got in the plane. These are just some fun pictures. Team pre-flight. Get everybody together. Get in the plane. And this is a little bit fun. I think this was online, but I'll just talk through it while it goes. So. There's some sweet music. Anyway, this is first flight right here. And those of you in the controls world, you can see the stingers on the wing and the tail. And we did a lot of calculations to determine our PIDs. We take the thing up in the air, and it's a little bit stable. We start to get more and more stable, and see how stable and beautiful that is? Then we start getting maneuvering flight. Can't do that in a fixed-wing airplane. Take off and just roll backwards and get out of dodge. It's really fun. Yaw rates. So these are some of those basic physics things. How much torque are you putting in? What's the moment arm? How fast can we turn in yaw? Side slips. This particular side slip actually ended in vortex ring state. At just over 100 feet coming in, came down against the rotors and flew into the wake and had to side slip out of it. This is, I don't know, 10 degrees forward. You can see the double slotted high droop in the flaps to change the chord angle. So as these things tilt forward, it gets to the point where you're downwashing in the wing. You want to get that chord angle as high as possible, mean chord angle. This is our, I think, our 100th flight. Taking the thing off, it was so fun to fly that we found an excuse to fly it every time we could. This video, unfortunately, is almost a year old, so it's a lot of vertical flight. We've been moving further and further forward and getting on the wing, so getting fast enough with these things coming down. We have full down to 0 now, and we shut the power off and see if we can glide. I don't know how much more is this, but that's the vertical flight. This is really interesting. This guy that flies helicopters, right? Slope landing. What's the trick in a slope landing? Or slope takeoff, even better.
Trick.
The trick. I mean, okay, so it's a trick question. No, it's not. You got to remember that the disc of the helicopter isn't fixed frame with the base of the helicopter. So if you're going to take off on a right slope here, as you start to pull up that collective, you're going to start to move your cyclic to the right. And you're naturally going to start to pick up that left skid. But what's happening to the disc has gone level, and then the disc comes straight up, right? You can't do that in a fixed frame aircraft, right? So how do you land in a slope or in a crosswind? Do you land into the wind? So the wind's whipping. This is a 32 knot day. The wind's coming straight at me. And you've got a cast-ring nose wheel, and you've got brakes on your brakes on your main gear. And you say, well, obviously we always land into the wind, right? We've got more controllability with the weather vaning tendency of the tail, and all of a sudden you can't put it down. Because every time you put down the cast-ring nose wheel and you start to drop the back, you start whipping backwards. And the worst thing to do is going backwards when you land. That's just not a good position to be in. So as we're doing this, and you guys are way smarter than me, you probably would have predicted this. I didn't. And I got up there and I was like, holy shit, I can't put this thing down. And I had to turn this thing about 45 degrees, lock the right brake, put the wheel down, and then as you let this down, you can't keep the rotor disc over as you gently let it down like you do in a helicopter. You have to rethink how you're landing. So autonomous aircraft, eVTOLs, they're kind of synonymous in many circles. And you start to think about writing a auto landing sequence, and you start to totally change your perception of how we're going to approach the helipads. This was a fun day. We did have a fire in the cowling during flight. It's pretty scary. You're up there, you start to smell strong electrical fire, and we were able to land it, pop in. This is just to remind us that real shit happens. That particular issue is because I didn't properly review a design where we had an electrical connection that in the stack up had some polymer in it, and it got hot, it reduced decreased the contact resistance, something got hot, caught on fire, things shut down, put the thing back together. These were fun tests. We got up in a stabilized out-of-ground effect hover, and remember, we claimed to ourselves that we could lose any motor and we could still land safely. But it takes a fair amount of gonads to be up there and be like, you know what, I'm gonna now shut that down. And you start to fall, because you're gonna have an uncontrolled yaw, but you're gonna lower down, and you're gonna keep the rubber side down. And you see how close the prop is to the ground there? It's about 4 inches off the ground, but we were able to achieve that. This right here was another pretty nasty landing, where we had a test device on the dashboard measuring high fidelity CAN messages, and it fell off and it severed both IMUs at the same time. So both IMUs are gone. You've got no inertial measurement, so now you have an open loop control. And what do? Just kill the batteries. You got to come down, right? So we landed on the tail, took out the me and Ava, that's the we. Put it back together, got it flying. So let's say you want to fly from airport to airport to airport. You want to refuel this thing. How are you going to do it, right? So this is Ike Riley. He's a rocker. He's a great guy, but he sold us his 1982 Eagle bus, and we put a helipad on top of it. We opened it with solar. We put a 45 kVA generator down in the back and a 1,000-volt, 100 kilowatt AC to DC converter, because we need to have 1,000 volts DC nominally to recharge the aircraft. And everybody knows battery charging, you can't just dump a bunch of current into the things blindly. You have to have a queue communication between your battery monitoring system and the aircraft. So this is Martine, our partner and sponsor and a friend, just checking off the test flights. Tethered hover, landing and pickup, free hover testing, free hover out of ground effect, in ground effect, OEI testing, ground initiated transitions, hundreds and hundreds of flights just getting through them. This, I don't know what vector angle we're at there, maybe 20 degrees forward. We've gotten up to about 75 knots forward, which gets us on the wing. And that's inspired us to design a new aircraft. And the new aircraft is using the same first principles engineering. An electric vertical takeoff and landing aircraft, energy storage, specific energy density. Diesel Jet A, 100 low lead, it's not getting any more energy dense. And everybody's giving high fives to each other at Boeing when they get 0.4% better efficiency, right? Because that's pretty damn good. But specific energy density of batteries moving 5 to 8% per year, right? So there's going to be a point where it comes to parity. Anybody know the efficiency of a jet engine, roughly 20, 25, 30, right? Reciprocating engine, maybe about that. Really, really good ones, maybe higher. But the conversion efficiency, battery to propulsion in electric, what do you guys think? Take a guess. What's that?
95.
Not quite that much, but close, very close. I mean, if you're in the 90s, you're doing a really, really good job. The propulsive efficiency of the propeller is obviously kind of tearing both of them down. But that specific energy density of batteries is going up. Jet A and low lead is here. We're 20 times different right now, but our conversion efficiency is maybe a 3 to 1 or 4 to 1 difference. So maybe 5 to 1 difference right now. But we're still going up 5 to 8% year-to-year compounding. Obviously, the power conversion propulsion design consumes that specific energy density. The more battery you can get in there because you have lower empty weight fraction, gives you a better aircraft. And of course, your L over D determines if you're operating, in a good portion of that curve. It gives you effectively those 4 parameters give you the range of the aircraft. To make practical electric aircraft, we have to thread those things together very, very carefully because a lot of times, aerodynamic efficiency doesn't support empty weight fraction, right? So we want a nice, long, big wing, and we're like, whoa, that's got, small thickness ratios. If you have a 100-foot wing and a glider, empty weight fraction kind of goes to crap. So let me just look here. Am I okay on time? You guys getting bored? No. This is how Beta was founded. And this is the path we're on right now. Now we're up to about 30 people, and we have found ourselves in a really, really unique position, all because of that one little comment about, I'm here because I just like aviation. And we're going to elicit critical thinking in aviation by building something. And while a lot of folks create a big stack of papers as a design study, which are awesome, super interesting to read, but it doesn't fly. And we found ourselves, a little company in Vermont, in an awesome position, competing with all the big guys in this next design and having a pretty sweet customer and contracts for building these aircraft. So I think that's all I have for a presentation. Apologies, it wasn't super academic, but just wanted to kind of tell a story that was my own little personal path after Lockheed asked me to come down here to where we are as a business, and now it's grown from this little kernel to a team that's just awesome, and we're having a lot of fun, and we're flying everything every day. I've tried to fly a different aircraft every day of the week, which is just like I've never dreamed of something quite as fun, and hopefully, well not hopefully, by the end of this year, we'll be flying a 7,000-pound eVTOL that'll do 250 nautical miles, which I think is, we already flew the heaviest eVTOL ever, which isn't something to brag about in aerospace, I know, but just as like something. And now we're going to fly the longest range. So that's all I got. Any questions, thoughts, comments? Yeah.
But also how you manage the project management aspect of it, because it sounds like you got to iteration pretty quickly.
Sure, I'll start with the easy part. Whole project was 10 months long. We went through probably 8 weeks of design turn at the beginning, figuring out what the heck we were going to build. And then by, and I'm just doing math in my head from 7 to 11, it took us 4 months to complete the Iron Bird. It took us 3 months to get that entire system kind of debugged. And then overlapped with that a little bit, it took 4 months to get the FAA to agree to allow us to fly it. And there's 3 aspects to a phase 1 flight testing authorization called a letter of authorization, or a program letter. 1 is the operational restrictions, like where and how you can fly something. 2 is the airworthiness, and 3 is the pilot licensing requirements. And the pilot licensing requirements were the big holdup. They said, okay, that's fine, I'll fly it over anybody's head, I don't care about the pilot or your testing, just do it over there. But then we went to them and said, who's allowed to fly this thing? Is it a helicopter pilot? Is it a fixed-wing pilot? Do they need a multi-engine rating? Do they need a high-performance rating? Do they need a complex endorsement? Like, what do they need to fly this? And they're like, well, obviously, they need a powered lift rating. Well, it turns out that the FAA, there's the notion of a powered lift in the military. There's no certified powered lift aircraft. Therefore, there's no practical test standards for a powered lift aircraft. They had issued 6 powered lift certificates to ex-Osprey pilots. They had since pulled them back, and for the 609 and a few other things, they were giving out specific letters of authorization to really experienced test pilots. And we said, well, that's a bummer, because we can't afford one of those guys. And we wrote a Part 141 style flight school curriculum, built the simulator, went back to the FAA, and after going to Washington, going to Portland, Maine, going to ACO down here in Boston, back and forth, we ended up going to our local senator, Senator Leahy, and saying, you've got to do something about this. And this is like, you know, social engineering. We go to the senator, we go to Bernie, we say, you've got to help us out. And they started putting pressure on the FAA. We talked to the commissioner of the FAA, who finally allows us to get our flight school accepted. And I think we're the only eVTOL company that can now issue letters of authorization to pilots to fly eVTOLs. So we have pretty neat. So I'll answer your second question now. Project management, as you might imagine, that's probably, that didn't come up. It just, when you get into the rhythm with a bunch of people who've done a lot of technical things before, somebody says, I'm going to deliver you a propeller. There's no Gantt charts or formalized bills of materials and purchasing departments and whatever else necessary to get it done. The person doing it does all of that. And in very fast, efficient prototyping teams, even now, when we've got a 30-person team, we don't have an ERP system, we don't have a purchasing department. You as the engineer are responsible for delivering a battery on June 15th. You got to get that all figured out, and there's no loss in translation between the supplier and the purchasing department and whatever. And we have quarterly goals, and that's it. There's nothing higher fidelity than that. And I fully recognize that at some point that has to change as our business starts to get, you know, proctology exams from the FAA and other things. But right now we really don't have the type of project management, and I hope there's nobody in here doing or teaching the project management or engineering management course. But I worked for Raytheon. I worked for a couple big companies. And we spent more time in prototyping, and this is very different than production. Because you can waste a lot of time in production if you're missing a control pin on the upper left corner of the aircraft, or it's sitting on the end of the line. But that's not the case in prototyping. Things change too quickly. So there really is no formal project management aside from people keeping their promises.
Changes, how do you manage communicating between different people who are responsible for different things? Because if you're trying to iterate very quickly, isn't it easy for something to be overlooked because something is someone else's responsibility?
Not in a really small team. So our company, even at 30 people, every morning, 9:15, we get around a big table and we hash out what everybody's doing that day. And we make sure people are responsible for particular elements. And another thing about the culture of our business, which will expose how this works, we have no vacation policy. Anybody can take any time off anytime they want, as long as they don't let their colleague down. So if they're working on a project with somebody else, they don't come to me and say, hey, can I take this time off? I don't care if they do. They go to their colleagues who are depending on them to create a connector that goes to the flight controller, that goes to the motor, and you say, work that out, and if you lose the respect of your colleague, you're out. And that's how we manage that. So people are operating with absolute accountability of keeping their promises. So again, that's something that works when everybody's touching and feeling everybody else. We've arranged even the desks in where we're working with people that are communicating with each other technically within the aircraft, such that they aren't more than 10 feet from the person who they're, if you're doing connectors and wiring, and that this guy's doing flight controllers, and this person's doing inverters, you're sitting between them. And there's no way around it. And we're shuffling that constantly. So I apologize for not having a good answer for you, but that's how we're rolling right now. Yeah?
You told us to test an app or a SIM to give the feedback.
Yes. So we've been quietly developing autopilots and synthetic vision and a whole bunch of things in an app called Xavion, X-A-V-I-O-N. And yesterday we released on the App Store the 3D instrument approaches. So everybody's probably familiar with instrument approaches, flying the needles, ILS is GPS with LPV. The 3D instrument approaches will actually put tunnels in the sky, showing you those step downs, showing you the glide slope so that your velocity vector is pointed at the airport no matter what altitude or direction you're flying, and that velocity vector is straight down a shot in synthetic vision. So we call these 3D instrument approaches. So no longer are you looking at this right here. You're looking at a tube that you're going to fly down. And I'm aware that there are hoops in the sky with other people, but this is a little bit unique in the way that it's set up. And yeah, if you guys want to, if you're out flying, test it out. Just take Xavion, throw it on your phone or your whatever, and get a Sirius or, not Sirius, excuse me, who's the guy that makes the ASB receivers, the really good Stratus, yeah. The Stratus, they seem to be really stable systems. Any other thoughts or questions? Yeah.
Can you talk about, I think I hate this question, but I might as well ask it. Can you talk about scaling or any sort of plans you have for that? Like, how do you scale up this very tightly in a team?
Yeah. So I have a goal to keep, the last business, or 2 businesses ago, we were at 325 people. And it got too unwieldy. It was too much growth, not enough camaraderie, things start to get the culture starts to break. And culture being absolutely paramount, as I described a second ago, within our business, how we operate. My goal is to keep it less than 40 people and have very, very high-performing engineers and giving them all the tools to be the most efficient engineer they can be. So instead of asking the question, who do we hire to do that? It's, can you figure out a way to make the time to do it yourself? Can we give you a tool to be more efficient? Can we offload you from something that can be outsourced? Making parts, it's great to get engineers building composite parts the first time. But once you do it once and you can speak the language, you understand the problems, you get it elsewhere. So step 1 is to not scale. Like, we're not pushing repeat on people. It's keep it tight and small. And then recognize what you're good at, right? What does success look like for us as a business? To me, it's not to grow to a $4 billion business making 200,000 or 2,000 aircraft a year. It looks like us getting to the point where we have that aircraft that now can be type certificated or is type certificated, and it gets handed off to people who enjoy clipboards and manufacturing and project plans. There's really good engineers. And by the way, within our team, there are 4 or 5 engineers that will transition over to that new team. So the scaling isn't trying to take a good engineer, a good development, research and development engineer, and saying, now you're going to manage production of that thing you designed 4 years ago. And they're like, oh, I want to design something new. That's how I roll, right? And the better thing is to hand that off, in my opinion. Now, there's certain people that will go with that, right? And so then the scaling will be a sidestep from the core team over here to build a team that now is good at production. And maybe do that 4 times, right? So the core team and what we're talking about here doesn't necessarily get very big, so we don't need to scale. And could be totally wrong, and that may be totally infeasible, but that's the plan right now. Yeah.
What resources did you use when you were stuck on a problem, especially since you're in Burlington, in Vermont?
Like technical resources or like human resources outside the company?
Technical and business
Yeah.
issues.
So we used a variety of different people that I had. So if you're talking about like stuck on a technical problem, how do we get over this specific hurdle? One was to call up, and I won't use names, but you can imagine the top 5 aerospace companies. Find the best person on LinkedIn that you can find designing propellers. Call them up and say, hey, we have this little project, it's up in Vermont. Can you help me out? Here's my problem. And it turns out that smart people, when they realize you are engaged and passionate and care about what you're doing, they'll answer your questions. And they could be the lead development engineer at pick one of the 5 top aerospace companies, and they answer the phone, cold call, and you say, I need a little bit of help on this. And that happened several times. We got stuck on, for example, the composite layups on top of the propellers. Talked to this guy, 70 years old, the guru at a national propeller manufacturer, and he's given me more insight about propeller manufacturing and where they bumped their head in the past than any book ever could. And you're describing and using them as a sounding board on every one of those little challenges. So just pick up the phone and call people. If you're nice and polite and professional to them, they answer your questions. We didn't use, if you're asking like, did we go to a local university and use their FEM models and whatever else, we didn't do any of that. Really, again, ask the team internally to find a way to make themselves efficient enough to solve the problems.